Good morning, guys. Welcome back to another week. I believe just 2 more weeks of assignments. Today will be the last one for seniors. So we are nearing the end. But today we're going to talk about heat of phase changes. So you read a little bit about this in the CK12 reading. Going to change things up a little bit from what they explained, or not really the concepts, but some of the calculations. First thing you have to understand is that anytime there's a phase change, so when an ice cube melts, or when water freezes, or any other substance melts or freezes, or boils, or condenses, there's an exchange of heat. You can't get from a high energy state like a gas to a lower energy state like a liquid, or certainly a solid, without giving away some of that energy that you had, that substance had as a gas. On the other hand, you cannot get from a low energy state like a solid up to a liquid or a gas without adding energy. So there always has to be an exchange of heat along with a phase change. So that's kind of what this is showing you, the different phase changes that can happen. You have some ice. If it's going to melt, it's going to go this way. We have to take in energy from the environment. If it's going to then evaporate or boil into vapor, into gas, you also have to take in heat from the environment. So those two are endothermic processes, melting and evaporating or boiling. And if we're starting with vapor and we're going this way, going from vapor to liquid, like the condensation that forms on the side of a can of soda on a hot day, that is going to be exothermic. The heat that the water vapor had when it was in the air has to be lost, has to be given away to the environment in order for it to cool down and form a liquid. Okay, so the amount of heat released or absorbed is going to depend on two things. How big is the sample, the mass of the substance, and then what is it? So some things are better, excuse me, some things take more heat per gram, or as the reading talked about, per mole, in order to melt or boil. Um, the amount of energy released or absorbed doesn't matter which direction you're going, and that's an important point to make here. So it talked about the fact, in the reading, it talked about the fact that there's like 6.01 kilojoules per mole of water would be required. So that many kilojoules of heat would be required to melt a mole of water. And the same amount of heat would be released if 1 mole of water were to freeze, because those are equal and opposite processes. So it's the same amount, it's just a matter of is it absorbed or is it released. In other words, if I have an ice cube in my hand and I take it out of the freezer and it melts to liquid, maybe not in my hand, maybe I should probably put it in a glass. So I have an ice cube, I put it in a glass, I set it on the counter, and I let it absorb heat from the environment and melt. Then I take that same mass, that same sample of water, and put it back in the freezer and refreeze it. The energy released, I'm sorry, the energy absorbed by the melting of the water would be exactly equal to the energy that is released when I put it in the freezer and it turns back into a solid. Because those are exactly opposite processes, they involve exactly the same amount of energy, same number of kilojoules. Okay, now the identity of the substance will that's gonna factor into its heat of fusion or heat of vaporization. And I'm going to give you different numbers because we're not going to go per mole. I'm not going to make you get out a periodic table and convert grams to moles and moles to grams. We're just going to go straight from grams to kilojoules, or actually grams to joules. Okay, so let's do an example problem here. Calculate the heat absorbed when 31.6 grams of ice at 0 degrees Celsius is completely melted. Anytime we have melting or freezing happening, we're going to involve a constant called the heat of fusion. And if we want to know how much heat is absorbed, so that's what the question is asking, how much heat is absorbed, that's still symbolized by Q. And if you remember our specific heat discussion, we used Q then too. But instead of having specific heat and mass and change in temperature, we're going to use a value called heat of fusion. The CK12 reading referred to this as molar heat of fusion because we were looking at kilojoules per mole of of our, in this case, ice, water. But we're going to actually call it just heat of fusion because we're going to do this in grams. It's going to make things a little bit easier, okay? So the amount of heat absorbed is going to be equal to the heat of fusion times the mass of the sample. So this is the equation that we're using, and it looks like we've been given the mass right there, right? So that's pretty easy. The heat of fusion will have to be provided for you, and I will do that. So it's actually 334 joules per gram, and that is specific to water. So anytime you're given a new substance, I'll give you the heat of fusion that we need to solve the problem. Okay, so there you go. You have the heat of fusion, you have the mass. Tell me how much heat is involved. Okay, so we are going to go ahead and, okay, so if you multiplied your heat of fusion, 334, by your mass, 31.6, you should have come up with a heat of 10,554 joules. And again, don't be too alarmed by the fact that that is a big number. Joules, of course, as we've been saying, are really, really small. Okay, let's try a different problem. Okay, so this is talking about condensation. So here we have water condensing this time. So it's not freezing, it's condensing. So we're going essentially from a gas to a liquid. If we go back up to our picture up here, heat of fusion involved these two processes, melting and freezing. Right now we're talking about condensation. So that is a little bit different. It's not going to be the same amount of heat that we had over here for melting and freezing. So the heat of fusion for a substance like water is the same whether you're freezing or melting. I said earlier that they're equal and opposite processes. So that 334 joules per gram for water would be the same whether we're melting an ice cube or freezing water into ice. Now, over here, though, we're talking about evaporation versus condensation, and the question is asking us about condensation. That amount is going to be different, and it's actually not called heat of vaporization anymore. Pardon me, it's not called heat of fusion anymore, it's called heat of vaporization. So we have a new equation that we're going to be using here, but it's essentially the same thing. It's just Q equals heat of vaporization times mass. Now the mass, of course, once again is given, right? The heat of vaporization for water is 2,260, so it's a much larger number, and that's going to be once again in joules per gram. So let's go ahead and see if we can calculate how much heat 40 grams of water would release as it condenses. Okay, so I got 90,400 joules. Notice, by the way, as we multiply here, since this is 40 grams as we're solving, that the grams would, in fact, cancel, right? So that's why you're left with joules as your answer. Again, big number, but that's okay because joules are small. All right, last question. What is the mass of methanol vapor? What mass of methanol vapor, condenses to a liquid as 20 kilojoules of heat are released? So let's start with our equation. So we're talking about condensation once again, so we're going to use our heat of vaporization. So that's our equation. This time, though, we're trying to solve for what? All right, we're trying to solve for mass. So we're going to rearrange our equation to say that mass equals what? Well, we got to rearrange. So if mass is being multiplied by HVAP, then to get mass by itself, we got to divide both sides by HVAP, or heat of vaporization. So mass equals, let me move this down a little bit. So mass equals Q over heat of vaporization. And so now we need to do two more things. Our kilojoules have to be converted to joules. So if you remember, what does the prefix kilo mean? Right, so it's 1,000. So instead of 20 kilojoules, we're going to convert that to joules by multiplying by 1,000. So we have 20,000 joules. And on the bottom, we just need the heat of vaporization for methanol, which is going to be provided. And that value is 1,103 joules per gram. So go ahead and punch that into your calculator, phone, whatever, and see what you get. Okay, and that gives me 18.1, and of course our joules cancel, and that leaves us with grams. All right, guys, so that is our discussion of heat exchange during phase changes, and we'll see you next time.